Today we're going to talk about LEDs. Nowadays, these amazing devices are used literally everywhere. So what are we gonna do today is learn to correctly power them without turning them to blue smoke. This is Ramatino. Let's see what we got here. Core interior lamp, a salvaged fragment of an LED 220 volts light bulb. These two parts also come from an E27 bulb. This is a piece of an LED strip marked DC 12 volts. This is a part of an LED scroller display. This is a fragment of a 220 volts GU10 LED bulb. There used to be a driver PCB here. This is a single LED. And this is just a diode, an electronic component. The first important thing you must understand is the difference between an LED and an LED-based lamp. We only got two LED lamps here, this and this. Why so? The answer is simple. Both the LED strip and the core interior lamp are powered by 12 volts. You cannot power an LED from 12 volts. When you see this listing on eBay or elsewhere that claims to sell you an LED that you can feed 12 volts to, this is actually not an LED, but rather a circuit built to supply regulated power to the internal LED, while you feed 12 volts to the circuit itself. Remember, LEDs do not have a voltage rating. In fact, the only parameter that's important to them is current rating. So, to power an LED, all you have to do is supply just enough voltage to come up with enough current. You must also ensure the current does not exceed the LED's maximum rating, because if it does, the LED will be toasted instantly. So what is an LED? Basically, it's yet another semiconductor device. Diode's schematic symbol is this. An LED is this, accordingly. What's special about any diode is that it exhibits a constant voltage drop, which can be measured with the help of a multimeter by putting it into diode mode. Here you can see diode symbol here, and a V voltage symbol here, which means the multimeter will be displaying not ohms, but volts, the voltage drop. Now I got this plain regular diode here. The display reads 0.68, which means this particular part's voltage drop is about 0.7 volts. Please note that diodes also have polarity, and it's quite easy to memorize. The triangle is the positive end, while the line is negative because it coincides with the minus sign shape. Back in school, in physics class, we were told that current flows from negative to positive, as current was believed to be the flow of electrons, which are negatively charged particles that are supposed to be attracted to the positive pole. However, in electronics, we use an opposite flow direction, which is from positive to negative. You can think of it that way. Positive pole has excess charge, which always tends to leave it. Hence, current flees from positive to negative. So this triangle arrow points in the current flow direction. Diode's positive pole scientific name is anode, and negative pole cathode. Most diodes have a cathode mark, so you can differentiate between poles. And it's also easy to memorize, since the negative, the minus sign, is also a line. So, to measure a diode, we must apply a multimeter's negative probe to the negative cathode mark. If we switch the probes, we can see no reading since the diode is off, or as they say, reverse biased, and current is not flowing. An LED is basically a fancy version of a regular diode, only as you pass current through it, it emits light. LEDs, however, usually exhibit a much larger voltage drop than regular diodes. Here we can see the universal component tester GM328 measure voltage drop across a blue LED. The value is usually within 1.5 to 3 volts range, and depends on semiconductor materials it's made of, or, rather, LED's emission color. In this table, you can see typical voltage drop values across diodes of different color. In theory, if we check this diode with the multimeter, we're supposed to get a reading of around 1.7 volts. In reality, however, this particular meter cannot check diodes because voltage across its probes is too low to turn on an LED. You can try it with your multimeter and see if it works. Usually, if you're up to checking LEDs, you'd better off using a 9 volts powered multimeter, as opposed to models that use a pair of AAA batteries. The higher the battery voltage, the higher the probe voltage. Some modern multimeters also have a separate mode for LED checking and use a built-in step-up converter to turn on LEDs. Now, we've established that voltage drop across the LED's terminals is constant. So, the LED acts as a kind of a regulator that strives to keep voltage across its terminals unchanged. If you attempt to raise the voltage, the LED will react by increasing current. This will prevent voltage raise. However, if you insist and apply, say, 12 volts to LED's terminals, the current will increase manifold, which will result in your LED burning out instantly. So, to power an LED, we need to use a step-down circuit which will keep the current strength within the LED's specified rating. And the easiest way to do it is use a resistor, which will limit current and allow excess voltage to drop. Here's the general circuit we want to use to power an LED. This is a typical serial connection, since all components are connected in series, and R is resistance. Current flows from positive to negative, passing through the resistor. As we, again, remember from physics class, current strength in a serial connection is the same over the entire circuit, since there is only a single pathway for the charge to flow. Current is represented with I symbol, which stands for intensity. Power supply voltage is represented by the U symbol. For your information, in the US they use V for voltage, which makes more sense. But as I am in Europe, I will use the designation used here. The U voltage, in our case, will be divided between the resistor and the LED. So let us designate LED's voltage as U1 and resistor's voltage as U2. Imagine we power our circuit from a 12 volts DC power supply. This means U will equal 12. Let's say voltage drop across our LED is 3 volts. This means U1 will equal 3, and U2 will equal 12 minus 3, which is 9 volts. And before we can use Ohm's law to calculate resistor value, we need to decide on the current we want to pass through our LED. Ideally, to answer this question, you must consult the datasheet provided by the manufacturer. So if you have one, please do use it. And if you don't, you're probably good starting with values from 10 to 20 milliamps for small LEDs and maybe from 50 to 100 milliamps for larger ones. If you're experimenting with extra bright and powerful LEDs like Philips Lumileds, for example, naturally, you're gonna have to use much bigger current values, but the rating, of course, you can find in the LED's documentation. Okay, enough with the theory. For starters, let us try to power this LED strip. I suggest we start with 100 milliamps of current, which is 0.1 ampere. Please keep in mind that all physics formulas use standard units, so if we're up to using Ohm's law, we have to specify voltage in volts, current in amperes, and resistance in ohms. Ohms, not kiloohms. So, if you have a 1K resistor, that would be 1000 ohms. Now let's do our calculation. R equals U divided by I. Mind you, we are doing calculation for the resistors part of the circuit, so we have to use the U2 value, which, as we already know, is 9 volts. current value is 0.1 amps. And this yields resistor value of 90 ohms. Good. I got this 12 volts power supply, but I decided to use a 150 ohms resistor, just to be on the safe side. As the current is inversely proportional to the resistance, larger resistor values produce lower currents. We do not know the actual working current value for this LED for sure, so we gotta take precautions. By the way, it's always a good idea to recheck the resistor, because sometimes they end up in wrong bags. If we look at this PCB carefully, we can see this wire goes to this pad, which means it's the positive terminal. I soldered an extra wire here, so we can use our multimeter to measure current. Let us find out what current we're gonna get with the new resistor value. The voltage drop across the resistor terminals is still 9 volts. Resistance is now 150 ohms. This means the current value will be 0.06 amps, that's 60 milliamps. The multimeter is set to current measuring mode, and wow, we got almost exactly the calculated current value. That's what I call science put to everyday use. And the LED is illuminating. Okay, let us now measure voltage. Supply is 12.4 volts. Resistor drop is 9.2 volts. And the LED voltage is 3.2 volts. Good. But our task was to use all the LEDs. We can see that diodes here are connected in series, so the schematics looks something like this. We have established that U1 equals 3.2 volts if we power a single LED. This means that 7 LEDs connected in series will exhibit 3.2 multiplied by 7, 22.4 volts drop. Obviously, our DC power source cannot supply this voltage. This means that even if we feed the 12 volts to the strip directly without using any resistors, the LEDs will not light up, since the supply voltage is way too low for the diodes to turn on. Let's see if it's true. The power supply is on, the voltage is present, but as expected, nothing happens. This means, to power all these LEDs, we have to connect them in a different manner. What we're gonna have to do is group them. But in our case, as we got a total of 7 LEDs, we can group them in 2 ways. Either by 2 or by 3. How do we decide? When wiring LEDs, you have to choose a connection scheme which yields resistors of lower value. Why is that? Well, because when you wire a resistor in series, some power is dissipated into heat. And the larger the voltage drop, the larger the power dissipation. Which basically means you're throwing your energy away. And that is actually the reason why most LED lamps use dedicated drivers to power LEDs instead of resistors. A driver is a high-frequency switched-mode converter that uses complicated circuit to step down voltage and regulate current. But let us get back to our task. Like I said, we need to group our LEDs correctly. What is the maximum number of LEDs we can power from 12 volts? If the drop across one diode were exactly 3 volts, in theory, we could power 4 LEDs. But it's 3.2 volts, which means we can only power how many? That's right, 3 diodes. Hence, we are going to wire them like this. 3 pieces in series with the resistor, and we have 2 identical circuits that go in parallel. The resistor here is placed at the negative terminal, and I guess it's obvious it can be placed at any part of the circuit as long as it is a serial connection. Why do we need 2 resistors? In theory, we could use this connection scheme and end up with a single resistor. Problem is, LEDs, just like regular diodes, have the so-called parameter spread, which means no two parts are the same. Say one LED may be rated for 3.2 volts, while the other for 3.18 or 3.22 volts, which means if you connect them in parallel, current flowing through each of the two circuits will be different, which will result in different brightness. However, if every circuit has an individual resistor, we compensate for the parameter spread because that allows current in each circuit to set individually according to LED voltage drop. Right. Now let us do the calculation. For the sake of simplicity, let us imagine we have only one circuit here. We have to multiply 3.2 by 3 because we got 3 diodes in series. That's gonna be 9.6 volts. We can think of these 3 LEDs as one large LED whose voltage drop is 9.6 volts. As our power supply voltage is 12.4 volts, the voltage drop across the resistor will be 2.8 volts. Current strength is 60 milliamps. R equals U divided by I. 2.8 divided by 0.06 is 47 ohms approximately. And now we just add another parallel circuit here. These two circuits will be fed the same voltage, but the current, as was noted above, will be slightly different. And we also use identical resistors because circuits are identical. To perform this connection, we're gonna need to make some modifications to the PCB. We got one extra LED here that we have no use for. Let us just unsolder it. Good. Now, according to our schematics, we are going to wire these two positives together, put resistors here, and also wire them together to connect them to the negative pole of the power supply. Power on. Looks like it works. Let us measure voltage on the LEDs. Oops. I think I shorted something with the probe and toasted an LED. As they are connected in series, one dead LED is enough to cut power to the entire serial circuit. Doesn't matter, you get the idea. Let us carefully measure voltages on the remaining LEDs. 3.14, 3.15. We do got some spread. 3.17 volts. One more thing to consider when using resistors to lower LED current. You have to realize that voltage drop across a resistor will cause it to heat up. This means you have to place resistors so that they do not touch anything, especially plastic parts or any parts that can, God forbid, catch fire. This also means you gotta pick resistors with appropriate power rating. Most resistors sold have power ratings specified by the manufacturer. To find dissipated power, we use this formula: voltage multiplied by current. As the drop over our resistor is 2.6 volts and current strength is 60 milliamps, power will be 150 milliwatts. But according to this table, the resistors we've used have 0.125 power rating, which is not enough for our purpose. It means the resistors are overloaded. And if we're up to building a step-down serial circuit, we need to buy resistors with higher wattage rating. Or, here's what you can do. Take two resistors and connect them in parallel. This will, first, lower resistance in half. Second, double the power rating. So, in our case, to come up with a 0.25 watts 50 ohms part, we need to use two 100 ohm 0.125 resistors. Okay, let us try to power this lamp. I tore it apart a while ago, obviously because it stopped working, which means some of these LEDs are dead. Let us first try to figure out the connection scheme. Yep, that's just 4 LEDs, again connected in series. If they are 3.2 volts diodes, the 12-volt power supply will not be able to forward bias them. Let us use the power supply with a resistor connected in series to find the faulty diode. I use the same 150 ohms resistor. There, here's the dead LED. And that's what we're going to do. We are going to solder the resistor in place of this LED. So we end up with the same schematic as on the strip. We will use the same 50 ohms, or rather 3 150 ohms resistors connected in parallel, which will yield the same 60 mA. Power on. What a great lamp. Okay, we also got these LEDs left. This used to be a 220 volts AC lamp. Here we got LEDs grouped by 3 and then connected in series. Here's the schematic. 7 LEDs in series, that means again, we cannot power this circuit from 12 volts. But we can power them if they are grouped by 3. Like this. This is gonna be 3 by 3. Power on. Working. Only some of LEDs are dead, shorted, but that's obvious. Okay, let us sum it up now. If we need to power an LED or a series of LEDs from a regulated DC power supply, all we have to do is use a resistor connected in series. The current passing through all the diodes in a serial circuit will be the same, while the excess voltage will be dropped on the resistor. The LED voltage drop is designated UD. It is also called diode forward voltage, and the diode, when it's on, is called forward biased. Safe LED current, in our case, is set at 60 mA, designated as ID. U is our power supply voltage and is equal to 12 volts. UR is the amount of voltage dropped on the resistor. To calculate it, we must subtract LED voltage drop from the power supply voltage. The LED voltage drop can be found in its documentation. If you have several LEDs, you have to multiply this value by the number of the diodes. Once you know the resistor voltage drop, you can calculate its resistance using the Ohm's law. So here's our final formula. U is power supply voltage, UD is voltage drop on a single LED, N, number of LEDs, and I is current. So if we consider our today's setup, UD equals 3.2 volts, N equals 3, U equals 12.4 volts, and I equals 0.06 amps. And the answer is 47 ohms. Just to remind you, if you have no datasheet for your LEDs, you can use a reference voltage value from this table. As for the current, if your LEDs are small, you will be on the safe side setting current at 10 to 20 mA. If you're playing with diodes from an LED bulb, it's probably okay to feed them current from 60 to 100 mA. And please do not forget to use correct units for your calculations. And one more thing. If you end up with a negative value here, it means that you've got too many LEDs in series for the specified power supply voltage. Then you either have to raise the voltage or regroup the LEDs, as shown in this video. And that would be it for today. This was Ron Martino. If you like this video, please don't forget to comment, share and subscribe. I wish you a very fine day, and I'll see you later.